Look up. If you could see through the atmosphere, through the interference of the sun's light, through the dust of our own galaxy, if you could see the deep universe with your naked eye, you would see something extraordinary. The cosmic web. Billions of galaxies arranged in filaments and sheets and clusters, connected in a three-dimensional structure of incomprehensible scale and beauty. Light that has been traveling for billions of years, arriving at your eyes from galaxies that lived and died before our sun was born. It is the most complex and most beautiful structure that has ever existed, and it has a hole in it. Not a metaphorical hole, not a region where the light is dim, a genuine, spherical, 330 million light-year wide region of the observable universe where the galaxies are almost entirely absent. A super void so enormous that the Milky Way could fit into it over 1 trillion times. A region of space that, if you were standing at its center, would show you almost nothing in every direction for hundreds of millions of light years. It has a name. Astronomers call it the Boötes Void. The general public, when they first encounter it, tend to call it something else. The Great Nothing. Here is something that most discussions of the Boötes Void never tell you. The void is not a distant abstract curiosity. It is not something so far away that it is irrelevant to our cosmic neighborhood. It is 700 million light-years from Earth. In cosmic terms, that is a modest distance. If the observable universe were the size of Earth, the Boötes Void would be about 100 kilometers away, close enough to study in detail, close enough for its existence to raise real questions about the structure of the universe we inhabit. And here is something even more unsettling. The Boötes Void is not the only void that matters to our cosmic story. We are living inside a void ourselves, a much larger, less extreme underdensity called the KBC Void, or the local hole, that extends for roughly 2 billion light-years around our position. The Milky Way, the Sun, the Earth, all of it sits inside a region of the universe that contains significantly less matter than the cosmic average. We are not observers looking at the great nothing from outside. We are void dwellers looking at the most extreme example of the phenomenon we already inhabit. But we will come to that. First, let us go back to 1981, to a survey that was not supposed to find anything extraordinary, to the night the map of the universe broke. In the late 1970s and early 1980s, cosmology was in the middle of a revolution. For most of the 20th century, astronomers had assumed that galaxies were distributed more or less randomly through space, scattered through the universe like raisins in a pudding, roughly evenly spread with local clustering, but no large-scale pattern. This assumption was comfortable. It was consistent with the cosmological principle, and it was wrong. The technology that began to shatter this assumption was the redshift survey. By measuring the redshift of a galaxy, how much the wavelength of its light had been stretched by the expansion of the universe, astronomers could calculate its distance from Earth. Do this for hundreds or thousands of galaxies in a systematic way, and you begin to build a three-dimensional map of the universe. Not just a two-dimensional image of the sky, but a genuine spatial picture of where everything is in 3 dimensions. Robert Kirshner was a cosmologist at the University of Michigan. Later he would become a professor at Harvard, one of the world's leading experts on supernova, and a key figure in the discovery of dark energy. But in 1981, he was part of a team conducting a systematic redshift survey, measuring the distances to galaxies in a carefully chosen set of fields across the sky. The goal was to build a more complete 3-dimensional picture of the local universe and study how galaxies were distributed on large scales. The survey was methodical and unglamorous. Galaxy by galaxy, Redshift by redshift, the map was being built. And then, in the data from 3 separate fields in the direction of the constellation Boötes, something strange appeared. In all 3 fields, separated from each other by 35 degrees on the sky, there was a gap in the redshift distribution, a range of velocities corresponding to distances of roughly 700 million light-years from Earth, where essentially no galaxies appeared. This was peculiar. In a random distribution of galaxies, you expect some fluctuation, sometimes a few more galaxies than average in a given volume, sometimes a few fewer. But to find a gap in all 3 independent fields at the same distance range spanning 35 degrees of sky, that was not the kind of fluctuation you expected. The probability of that happening by chance in a uniform galaxy distribution was very small. Kirshner and his team published their finding in 1981. They described a void of unprecedented scale, a region extending over roughly 50 million kilometers per second in velocity space, corresponding to a physical size of several hundred million light-years, in which the galaxy density was far below the cosmic average. They were careful in their language, noting the limitations of the survey and the possibility that they had happened upon a rare statistical fluctuation. But the astrophysicist Greg Aldering, who was a graduate student at the time and would spend years studying the Boötes Void in detail, described the initial reaction in the community with characteristic directness. He said that when the result was first presented at a conference, many researchers assumed it was a mistake. The initial reaction was basically disbelief. A void this size just did not fit into anyone's picture of what the universe should look like. The follow-up investigation took years. The initial 1981 survey had used 3 narrow pencil beam observations, like 3 narrow windows looking out into the universe. To confirm the void and establish its full extent, a much more comprehensive survey was needed, measuring the redshifts of galaxies across the entire angular area of the putative void. Kirshner and colleagues conducted this follow-up survey in the mid-1980s, measuring the distances to 240 bright galaxies spread across the relevant region of sky. The results were published in 1987 in the Astrophysical Journal. They confirmed the void and established its basic properties. Of the 240 galaxies surveyed, none had redshifts in the range corresponding to the void, approximately 12,000 to 19,000 kilometers per second. In a uniform distribution, you would expect 31 out of 240 galaxies to fall in this range. Finding 0 was not a statistical fluctuation. The void was real. The 1987 paper established what became the canonical picture of the Boötes Void, a roughly spherical region approximately 330 million light-years in diameter, centered roughly 700 million light-years from Earth in the direction of the constellation Boötes, in which the density of galaxies was far below the cosmic average. Initially, Kirshner's team called the region simply the Void or the Gap. Other astronomers began calling it the Boötes Void after the constellation in whose direction it appeared in the sky. A few writers, struck by its emptiness, began calling it by a different name, a name that, once coined, was impossible to improve upon: the Great Nothing. To understand the Boötes Void, you first need to understand what a void is, and what it is not. A cosmic void is not a black hole. It is not a tear in the fabric of space. It is not a region where the laws of physics are different, where time runs strangely, or where strange forces operate. A cosmic void is, in its essence, simply a region of the universe that contains less matter than average. Specifically, much less matter than the surrounding cosmic web. The universe's matter is organized into the cosmic web. the large-scale structure of filaments, sheets, galaxy clusters and voids that we have discussed in previous documentaries in this series. In the cosmic web, the vast majority of galaxies are concentrated in the filaments and at the nodes where filaments intersect. These are the overdense regions. Between the filaments, occupying the volumes that the galaxies have mostly evacuated, are the voids. Voids, in this sense, are defined by what they lack rather than what they contain. They are identified not by any physical object within them, but by the absence of galaxies in a region that, based on the average density of the universe, should contain many more. A void is the negative space of the cosmic web, the empty room between the furniture. Most cosmic voids are not completely empty. Even the deepest supervoids contain some galaxies. They are underdense rather than truly empty. The typical void contains about 20 to 30% of the average galactic density of the universe. If the surrounding cosmic web has, on average, one galaxy per 10 million light-years, a typical void would have one galaxy per roughly 30 to 50 million light-years. Still very lonely, but not absolutely barren. Voids vary enormously in size. The smallest cosmological voids are a few tens of millions of light-years across. Typical voids run from 30 to a few hundred million light-years in diameter. The Boötes Void, at 330 million light-years, sits at the large end of the distribution, significantly larger than most voids, which is why it earned the designation supervoid. It is what cosmologists call a statistical outlier, not impossible within standard models, but at the extreme tail of the expected void size distribution. How do voids form? The answer lies in the same gravitational process that builds the filaments and clusters. In the early universe, the distribution of matter was nearly uniform, but not perfectly so. Tiny density fluctuations, fractional differences in density that would be invisible to any observer at the time, were seeded during inflation. As the universe expanded and gravity acted on these fluctuations, the overdense regions grew denser while the underdense regions grew emptier. Matter flows from void interiors toward the filaments. Galaxies that form near the edges of a void are gravitationally attracted toward the overdense regions outside. They flow outward along the void boundary and accumulate in the surrounding filament structure. The interior of the void becomes progressively emptier as galaxies migrate toward its edges. The void itself expands because the underdense interior exerts less gravitational pull on surrounding matter than the cosmic average. The void effectively pushes matter away from its center through what physicists call a void outflow. This process, the formation of voids through the evacuation of matter by gravity over cosmic time, is reproduced by computer simulations of the universe. Within the Lambda CDM framework, run a cosmological simulation with the right initial conditions, let it evolve for 13 billion years, and voids of the right size, shape, and distribution appear in the output. The existence of voids is not controversial. The cosmic web, including its void component, is one of the great successes of modern cosmological modeling. What is controversial, or at least puzzling, is the specific properties of the Boötes Void. Its size is at the very edge of what standard models produce. Its depth, the degree to which it is underdense relative to the cosmic average, appears more extreme than typical simulated voids, and its internal structure, including the arrangement of the 60-odd galaxies that do reside within it, raises questions about exactly how this particular void formed and evolved. Voids also have an important dynamic property that distinguishes them from ordinary empty space. They expand, not just passively, as the overall universe expands, carrying everything within it, but actively. A void expands faster than the average expansion rate of the universe because the underdense interior has less gravitational pull to resist the expansion. Matter near the void edge flows outward, enlarging the void over cosmic time, and there is a force that accelerates this expansion dramatically. Dark energy. We will come back to dark energy and its relationship with voids in detail. But first, let us visit the Boötes Void directly. Let us imagine what it would actually be like to exist inside it. Close your eyes for a moment. Imagine that you have been transported, instantaneously, impossibly, to the center of the Boötes Void. You are in a spacecraft, floating in space. The life support is running. The windows are clear. You look out. What do you see? Darkness. Not the darkness of a moonless night on Earth, with thousands of stars visible and the Milky Way as a luminous band across the sky. Not the darkness of deep space near Earth, with planets absent and only stars filling the view. A different kind of darkness entirely, a darkness that is almost absolute. If you were at the center of the Boötes Void, the nearest galaxy to you would be hundreds of millions of light years away, hundreds of millions. Even at that distance, it would appear not as a bright object, but as a faint smudge, barely distinguishable from the background noise of the most sensitive optical telescope. With your naked eye, you would see almost nothing. No stars. There are no individual stars visible from that distance. No galaxy structure, too far away, too faint, just the deepest black you have ever experienced, punctuated by a small number of barely visible smudges at the extreme range of naked eye perception. If you had the best telescope that human technology has produced, say, the James Webb Space Telescope, you would do better. You would resolve some of those faint smudges into actual galaxy structures. You would see that they are real, that they contain stars and gas and dark matter halos, that they are building and evolving according to the same physics that operates everywhere in the universe. But they would be sparse, extraordinarily sparse. On Earth, when we look at the night sky, we are seeing a region of the universe with a typical galactic density, the cosmic average, roughly one galaxy per 10 million light-years of separation on average, with much higher densities in clusters and lower densities in ordinary voids. Our night sky, seen without the interference of the atmosphere, would show us galaxies in almost every direction. The Andromeda Galaxy, visible to the naked eye, many more resolvable with binoculars, billions more revealed by telescopes. From the center of the Boötes Void, the nearest equivalent of our local group, a small cluster of perhaps 30 to 50 galaxies, would be hundreds of millions of light-years away in any direction. In between, almost nothing. The cosmic web that surrounds the void, and that would eventually pull you back toward itself if you traveled far enough. That web would be completely invisible to you from the center. Too far away, too faint. You would be surrounded by a shell of near-nothingness extending in every direction to the horizon of the void. Astronomers have calculated that if you were at the center of the Boötes Void, you could see fewer than one galaxy per billion cubic light-years. Fewer than one galaxy per billion cubic light-years. On Earth, in the cosmic web, the average density is roughly 100 galaxies per billion cubic light-years. The Boötes Void is approximately 100 times less dense than the cosmic average, not completely empty, but astonishingly sparse. There is a psychological dimension to this that pure statistics cannot capture. Human beings evolved to process absence. The absence of sound triggers alertness. The absence of movement suggests threat. The absence of light tells us it is night. These responses are appropriate because in our evolved environment, Absence usually means something. Predator hiding, fire extinguished, prey gone. The Boötes Void is an absence so complete, so all-encompassing, and so permanent that nothing in human experience provides a reference point for it. An analogy might help. Imagine standing in the middle of the Sahara Desert at midnight, with no moon, no stars visible due to an overcast sky, total darkness, no sound except the wind, no light except perhaps the faintest glow on a very distant horizon. Now, multiply that emptiness by a factor that makes the Sahara look like a busy city street, and then maintain that emptiness in every direction, above, below, left, right, backwards, forwards, for hundreds of millions of light years. That gives you a fraction of the psychological reality of being inside the Boötes Void. But here is something important to understand. From the center of the Boötes Void, you would not be able to see the cosmic web that surrounds it. The filaments and clusters that define the void's boundaries are too far away and too faint for naked eye detection. You could not look outward and see the bright walls of the void. You would have no visual evidence that you were inside a bounded structure rather than simply in an exceptionally empty region of an infinite homogeneous universe. If humanity had evolved inside the Boötes Void, if the Milky Way happened to sit at its center rather than in the cosmic web, our picture of the universe would have been radically different. We would have looked up at the night sky and seen almost nothing. Our earliest astronomical observations would have revealed not the rich tapestry of the Milky Way, but a near-empty sky. The idea that the universe was densely populated with galaxies would have been, to those void-dwelling astronomers, as surprising and counterintuitive as the Boötes Void is to us, which raises an unsettling question. What else are we missing by being positioned where we are? What structures and patterns of the universe are we unable to see, or misinterpreting, because of the particular cosmic neighborhood in which our galaxy sits? The answer turns out to be deeply relevant, and we will explore it in detail when we discuss the KBC Void later in this documentary. But first, let us look more closely at the galaxies that do exist within the Great Nothing. The Boötes Void is not completely empty. This is an important point that is often glossed over in popular discussions, which tend to describe the void as a region of absolute nothingness. It is not. It is a region of extreme underdensity, far below the cosmic average, but not zero. Approximately 60 galaxies have been identified within the boundaries of the Boötes Void. 60, in a region where, based on the average density of the universe, you would expect to find approximately 2,000 galaxies of detectable brightness. A density of about 3% of the cosmic average. Not nothing, but 3%. Less than one galaxy for every 30 that should be there. The galaxies that do live in the Boötes Void are strange, not in their physics. A galaxy is a galaxy, governed by the same gravitational, magnetic, and nuclear processes everywhere in the universe. But in their situation, they are isolated to a degree that is almost incomprehensible. The nearest galaxy to any given void galaxy inside the Boötes Void is typically hundreds of millions of light years away. For comparison, the Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light-years from the Milky Way. This already feels like an enormous distance from a human perspective, but it is, cosmically speaking, a neighborhood. The Milky Way and Andromeda are gravitationally interacting. They will eventually merge, billions of years from now. A galaxy inside the Boötes Void has no equivalent companion. The nearest comparable galaxy is not 2.5 million light-years away, but 500 million light-years away, 200 times more distant. There is no gravitational interaction to speak of, no tidal influence from a companion, No chance of a merger or a close encounter over the age of the universe. Void galaxies are not just alone. They are alone in a way that has no analogue in the cosmic web. This profound isolation has consequences for the galaxies themselves. Galaxy evolution, the process by which galaxies change their properties over cosmic time, is strongly influenced by environment. Galaxies in dense clusters interact with each other and with the hot intracluster gas. They can acquire gas through mergers, strip gas from companions through tidal forces, be starved of fresh gas by the cluster environment, or be enriched by the supernova remnants of previous stellar generations in nearby galaxies. The environment shapes the galaxy. Void galaxies, lacking all of this environmental influence, are in a sense the purest laboratories for galaxy physics. They evolve almost entirely under their own internal processes, without the complicating influence of neighbors, tidal forces, mergers, or cluster environments. For cosmologists interested in understanding what a galaxy does when left entirely to itself, void galaxies are uniquely valuable test subjects. Studies of void galaxies have found that they tend to be younger than average. They contain more young, blue stars and have higher specific star formation rates per unit mass than galaxies in denser environments. This is consistent with a picture in which void galaxies have not had their gas supply exhausted by environmental effects. In a dense cluster, many galaxies have had their gas stripped away by interactions or by ram pressure from the hot intracluster medium, shutting down their star formation. Void galaxies, untouched by such processes, can continue forming stars at their own pace, using the gas they were born with. The 60-odd galaxies of the Boötes Void are predominantly low luminosity objects, smaller, fainter systems, rather than the massive spirals and ellipticals that dominate the galaxy clusters of the cosmic web. This is partly a selection effect. Brighter, more massive galaxies are easier to detect in surveys, and the surveys that have been conducted within the void are not sensitive enough to find all the dwarf galaxies that might be present. It is estimated that there could be many more dwarf galaxies in the void that have simply not been detected yet. WST has begun to change this. With its extraordinary sensitivity in the near and mid-infrared, JWST can detect much fainter objects at a given distance than any previous telescope. Deep field observations within and around known voids have begun revealing populations of faint dwarf galaxies that were invisible to Hubble and other previous instruments. This is an active area of research. As of 2026, the full census of galaxies within the Boötes Void remains incomplete. There may be substantially more galaxies within the void than the 60 currently catalogued, simply waiting to be found with deep enough observations. The arrangement of the 60 known galaxies within the void is itself instructive. They are not randomly distributed throughout the void's interior. Instead, they show a tendency to cluster near the center of the void and, to some extent, along a roughly cylindrical region that extends through the void. This internal structure, a weak filament threading through the interior of the void, suggests that even within the great nothing, the physics of the cosmic web is operating at a lower intensity. Gravity is still pulling matter together into small-scale structures. The void is not truly featureless. It is a more dilute version of the web that surrounds it. These galaxies are, in a sense, the survivors. The matter that was not efficiently evacuated from the void by the outflow that formed it. The residue of a process that removed most of the mass from this region of space over billions of years. But why did so much mass leave? What drove the formation of a void this large, this empty, this extreme? The answer requires us to look at what we know about how voids form, and to confront the honest truth that the Boötes Void even after more than 40 years of study, is not entirely explained. The most conservative explanation for the Boötes Void is that it is a statistical fluctuation, an extreme but not impossible outcome of standard lambda CDM gravitational physics operating over 13 billion years. In this view, the Boötes Void formed exactly the way all voids form. Matter evacuated from an initially underdense region under gravity, flowing outward toward the surrounding overdense filaments, leaving behind a progressively emptier interior. The question is whether the standard model can produce a void this large and this empty. The answer from simulations is probably yes, but at the extreme edge of the distribution. Cosmological simulations of a lambda CDM universe do produce supervoids comparable to Boötes. The illustrious TNG simulation, one of the most sophisticated cosmological simulations ever run, produces a distribution of void sizes that includes objects comparable to Boötes. The probability of finding a void of this size in a given volume of universe is low, but it is not zero. The challenge is that the Boötes void is not just large, it is also unusually deep. The ratio of the void's interior density to the cosmic average is lower than typical simulated voids of the same size. A standard void of 300 million light-years diameter would typically contain perhaps 15 to 20% of the cosmic average density. The Boötes void contains approximately 3%. This combination, large and deep simultaneously, is more unusual than the size alone, and harder for the standard model to reproduce naturally. One proposed mechanism for the formation of unusually large voids is the merging of smaller voids. In the early universe, many small voids formed simultaneously, regions slightly underdense relative to their surroundings that began to evacuate their matter. As these small voids expanded over cosmic time, neighbouring voids could merge, combining their volumes into a single larger void. The merger of smaller voids is the current leading explanation for the formation of supervoids in general, and is specifically invoked for the Boötes void. The void merging model predicts a specific signature. Galaxies within the merged supervoid should be found preferentially in a roughly cylindrical arrangement along the merger axis, the direction along which the smaller voids joined. The internal structure of the Boötes void, with its tendency for galaxies to cluster near the center and along a roughly linear feature, is qualitatively consistent with this prediction. But the agreement is not precise enough to confirm the model. Definitively, a second explanation involves the role of primordial non-Gaussianity, deviations from the simple Gaussian random field of density fluctuations predicted by the simplest inflationary models. If inflation produced a non-Gaussian field with more extreme underdensities than the standard prediction, large voids like Boötes would form more easily. Several theoretical papers, including a 2025 preprint specifically, analyzing the Boötes void as a probe of primordial structure formation, have explored whether the void's properties are consistent with non-Gaussian initial conditions. The 2025 paper, published on ResearchGate in November 2025, entitled The Boötes Void, a Cosmological Outlier in a Probe of Primordial Structure Formation, concluded that the void challenges the standard lambda CDM model through its sheer volume, paucity of galaxies, and morphological smoothness. The authors argued that the Boötes void's properties were consistent with formation under non-Gaussian initial conditions, or alternatively with early dark energy, a hypothetical component of dark energy that was more significant in the early universe than it is today. They suggested that the void may encode subtle fingerprints of inflationary physics, essentially that the unusual depth and smoothness of the Boötes void may be a remnant imprint of the conditions during the first tiny fraction of a second after the Big Bang. A third, more exotic explanation, which most cosmologists regard as speculative but which occasionally surfaces in discussions, involves the idea that the void might be related to a topological defect from the very early universe. In some models of the early universe, phase transitions in the first fraction of a second could produce defects, cosmic strings, domain walls, or other large-scale topological features that subsequently influence the distribution of matter. A void of the Boötes size could conceivably have been seeded by such a defect if one happened to be present in the relevant region of the early universe. Most cosmologists consider this explanation unlikely. The evidence for topological defects in the current universe is very weak, and the standard inflationary paradigm generically erases most defects by diluting them to unobservable densities. But the possibility illustrates the range of hypotheses that the Boötes Void's extremity has inspired. A fourth explanation involves what might be called a measurement bias or detection bias. The surveys that have mapped the Boötes Void have primarily been sensitive to bright galaxies, the massive luminous systems that are easiest to detect at large distances. If the Boötes Void contains a large population of small, faint dwarf galaxies that existing surveys are not sensitive enough to detect, the true galaxy density within the void might be higher than the census of 60 galaxies suggests. The void would still be underdense, but perhaps not as dramatically underdense as the current measurements imply. This is where JWST becomes directly relevant. If JWST's deep field observations within the Boötes Void reveal a substantial population of dwarf galaxies that previous surveys missed, the effective depth of the void would need to be revised upward. It would be less extreme than currently estimated. Early JWST observations of void environments have indeed found more faint galaxies than Hubble-based studies suggested. Whether this resolves the Boötes Void anomaly or merely reduces it remains to be determined as more observations accumulate. The honest assessment is that, while the Boötes Void is most likely a statistical extreme of standard, gravitational void formation, amplified by void, merging and possibly by above average, primordial underdensity, the current observations do not definitively rule out the more exotic explanations. It may be a rare but allowed fluctuation. It may encode signatures of non-Gaussian inflation. It may contain a larger galaxy population than currently known. Or it may be genuinely more extreme than standard physics predicts, requiring new cosmological ingredients to explain. What is certain is that understanding the void requires understanding the force that dominates its dynamics. And that force is not gravity, it is dark energy. Dark energy is a property of empty space itself. It does not dilute as the universe expands. Unlike ordinary matter or radiation, which thin out as the volume of space increases, dark energy maintains a constant density per unit volume. This means that as the universe grows and space expands, the total amount of dark energy in the universe increases. And since dark energy drives the expansion, a universe with more dark energy expands faster. The expansion is self-reinforcing. The universe accelerates as it grows. This has a direct and dramatic consequence for cosmic voids. Remember that voids expand faster than the average expansion rate of the universe, because their underdense interiors have less gravitational pull to resist the expansion. Add dark energy, the accelerating force, and the expansion of voids becomes even more dramatic. The void interior expands rapidly, driven by both the outflow of matter toward the edges and the dark energy-driven acceleration of the expansion. The interior grows emptier faster than it would in a universe without dark energy. More than this, dark energy has a long-term consequence for the fate of the cosmic web itself that is directly relevant to void science. As the universe accelerates, the expansion rate between any two objects that are not gravitationally bound to each other increases over time. Objects that are not currently bound, galaxies in different clusters, separated by void spaces, will eventually be accelerated away from each other faster than light, placing them beyond each other's observational horizon. They will become, in the most literal sense, forever invisible to each other. The void galaxies are the first to experience this fate. Separated from the cosmic web by hundreds of millions of light years, the 60 galaxies of the Boötes Void are already in a situation where most of the observable universe is receding from them at speeds approaching or exceeding the speed of light. Dark energy is pulling the cosmic web away from the void at an accelerating rate. The galaxies inside the Boötes Void are not just currently isolated, they are becoming more isolated as each billion years passes, over trillions of years, assuming the current understanding of dark energy is correct and its energy density remains roughly constant. The cosmic web as we know it will not survive. Clusters of galaxies will remain bound to each other, their local gravity sufficient to resist the acceleration. The Milky Way will merge with Andromeda and eventually with the other members of the local group. This merged galaxy, sometimes called Milky Way, will remain as a gravitationally bound island, but all other galaxy clusters will recede beyond the observable horizon. The universe will become, in the far future, a collection of isolated gravitational islands, each a merged remnant of a former galaxy cluster, surrounded by expanding emptiness that looks exactly like a cosmic void. The entire observable universe will eventually resemble, in some sense, the inside of the Boötes Void. This is not just a distant theoretical prediction. Voids are, in a very real sense, the future of the universe made present in specific regions of space. The interior of the Boötes Void today looks like what the universe as a whole will look like in the far future. The void galaxies are a preview of the fate of every galaxy that is not gravitationally bound to a cluster. Cosmic voids are therefore not just curiosities of the present universe. They are windows into the universe's future. They are regions where dark energy has already won, where the expansion has already evacuated most matter, isolated what remains, and begun the slow process of reducing the observable universe to a collection of gravitationally bound islands separated by featureless darkness. The horror of the Boötes Void is not just its current emptiness. It is what that emptiness represents about where everything is going. And this brings us to something deeply personal, something that should shift the way you think about your own cosmic position. We are already inside a void. For decades, astronomers noticed something puzzling about measurements of the universe's expansion rate. The locally measured expansion rate, determined by looking at the velocities and distances of nearby galaxies, was consistently higher than the value predicted by models calibrated to the cosmic microwave background. This discrepancy is the Hubble tension, which we have discussed in previous documentaries, and which has been growing more statistically significant with each new measurement. One proposed explanation for the Hubble tension involves where we are. What if the Milky Way happens to sit inside a large underdensity, a void, that has a higher than average local expansion rate? In a void, matter has been evacuating toward the surrounding filaments for billions of years. This evacuation creates a peculiar velocity flow. Matter near the void interior moves faster than the average cosmological expansion because it is being pulled toward the overdense regions at the void's boundaries. An observer inside such a void would measure locally higher expansion rates than an observer in a typical region of the cosmic web. In 2020, Moritz Hasselbauer and colleagues at the University of Bonn published a paper proposing exactly this explanation for the Hubble tension. They argued that the Milky Way sits within what they called the KBC Void, a large underdensity named for the astronomers Keenan, Barger, and Cowie, who had identified it in 2013. The KBC Void spans approximately 2 billion light-years in diameter, substantially larger than the Boötes Void, though less extreme in its depth. The interior of the KBC Void has a matter density roughly 30% below the cosmic average. Think about that. Not 70% below average, like the Boötes Void. Not 97% below average, 30% below average. A less dramatic underdensity, but spread over an enormous volume, and one that potentially affects every measurement we make of the local universe. Hasselbauer's paper proposed that the KBC Void explains the Hubble tension by causing locally measured expansion rates to be higher than the cosmic average. The argument runs as follows. The underdense interior of the KBC Void has been evacuating matter toward its boundaries for billions of years. This creates a systematic outflow. Galaxies in the local universe are moving away from the void center slightly faster than the pure cosmological expansion would predict, because the void outflow adds an extra velocity component. When we measure the Hubble constant locally, using nearby Tethys variables and type Ia supernovae as distance indicators, we are measuring a combination of the true cosmological expansion rate and this local void-driven outflow. The result is a systematically inflated local Hubble constant. This is a testable prediction. If the Milky Way is inside the KBC Void, specific signatures should be visible in the distribution and motions of nearby galaxies. The 2013 Keenan-Barger and Cowie paper that originally identified the KBC Void found evidence for a deficit of galaxies in the local universe extending to roughly 2 billion light-years, consistent with the void hypothesis. Subsequent analyses have confirmed the underdensity at various levels of significance. However, the KBC Void solution to the Hubble tension is contested. Other researchers have argued that the underdensity is not large enough or deep enough to produce the full magnitude of the observed Hubble tension, and that the hypothesis requires a void more extreme than current observations support. The debate remains active, and the 2026 precision Hubble tension measurements have intensified rather than resolved it. But regardless of whether the KBC Void fully explains the Hubble tension, its existence has a profound implication. We are not neutral observers looking at the Boötes Void from outside. We are void dwellers ourselves. The Milky Way, the solar system, the Earth, and every observation of the universe we have ever made has been conducted from inside a region of the universe that is less dense and differently structured than the cosmic average. This is not unusual in a philosophical sense. The cosmological principle tells us that no position in the universe is special, and that void dwellers and filament dwellers alike should, in principle, arrive at the same picture of the large-scale universe if they look far enough. But it is a reminder that local effects matter, that our cosmic address influences what we measure, how we interpret it, and what systematic errors might be present in our cosmological datasets. We are living in the interior of a void that is roughly 2 billion light-years across and 30% underdense. The galaxies around us in the local universe are systematically flowing outward, away from us, toward the denser regions of the cosmic web that define the KBC Void's boundaries. And those boundaries, when we reach them, include regions of significantly higher galaxy density. The knots and filaments of the web that we do not inhabit. The Boötes Void, in this context, is not a distant alien anomaly. It is an extreme example of the kind of structure we ourselves inhabit, taken to its logical extreme. The Great Nothing is the KBC Void with the dial turned up to maximum. A void so deep and so large that the 3% density of surviving galaxies within it makes even the most sparse regions of the KBC Void look richly populated. What does the latest science tell us about both of these structures? What have JWST, DESI, and the most recent surveys revealed about the nature of cosmic voids and their implications for our models of the universe? The study of cosmic voids has entered a new era in 2025 and 2026, driven by several converging developments in observational astronomy. The James Webb Space Telescope, operating now in its 4th year of full science operations, has begun contributing to void science in ways that were not anticipated when the telescope was designed. The Dark Energy Spectroscopic Instrument, mounted on the 4-meter Male telescope at Kitt Peak Observatory in Arizona, has produced one of the largest galaxy redshift surveys ever conducted, and Euclid, the European Space Agency's Wide Field Survey telescope launched in 2023, has added an independent view of large-scale structure, including void populations. WST's contribution to void science is primarily through its extraordinary sensitivity to faint, low-luminosity objects. Previous surveys of the Boötes Void and similar supervoids were limited by their ability to detect only the brightest galaxies within the void, massive spirals and ellipticals with enough stellar mass to shine brightly at several 100 million light-years distance. The smaller, fainter dwarf galaxies that might also populate the void were invisible to these surveys. WST's infrared sensitivity and spatial resolution allow it to detect galaxies roughly 10 to 20 times fainter than Hubble at a given distance. In early 2026, deep JWST pointings within and around the Boötes Void and several other supervoids have begun revealing a population of faint, compact dwarf galaxies that were previously undetected. A January 2026 analysis published in Science Times summarized these findings by noting that JWST deep field observations are beginning to uncover hidden populations within these voids, providing clues about formation processes. The implications of discovering more galaxies in the void are twofold. First, if the true galaxy count within the Boötes Void is substantially higher than the 60 galaxies currently in the catalogue, if there are, say, several hundred faint dwarf galaxies within the void that previous surveys missed, then the void is less extreme than it appears. The density deficit relative to the cosmic average would be smaller, and the Boötes Void might fall more comfortably within the range of structures produced by standard lambda CDM physics. Second, the faint galaxies within the void provide unique scientific value independent of the void's size. These are the most isolated galaxies in the observable universe. They have evolved without environmental influence for essentially their entire histories. Studying their stellar populations, star formation rates, gas content, and dark matter halos provides constraints on galaxy physics that complement studies of environmentally influenced galaxies in clusters and filaments. JWST's ability to study these objects in unprecedented detail is opening a new window on the physics of galaxy evolution in extreme isolation. The DESI survey is contributing from a different direction. DESI is conducting the largest spectroscopic survey in history, measuring precise redshifts for tens of millions of galaxies and quasars across 1/3 of the entire sky, to depths reaching several billion light years. This unprecedented dataset is being used to construct the most detailed three-dimensional maps of large-scale structure ever produced, including the distribution and properties of cosmic voids. Preliminary results from DESI, released in 2024 and 2025, have produced the most precise maps yet of the cosmic web's void structure. These maps show the Boötes Void and surrounding region in greater detail than previous surveys, and are being used to test void formation models, constrain dark energy properties, and examine the Hubble tension in the context of the KBC Void hypothesis. The DESI data are also contributing to searches for the signature of primordial non-Gaussianity in the distribution of voids, the fingerprints of inflationary physics that the 2025 Boötes Void paper argued might be encoded in the void's properties. One of the most interesting applications of the DESI void catalogue is in dark energy constraints. Cosmic voids are, in an important sense, dark energy detectors. The expansion rate inside a void, measured through the peculiar velocities of galaxies near the void boundary, is sensitive to the properties of dark energy. If dark energy is a simple cosmological constant, void expansion rates follow a specific pattern. If dark energy is dynamic, if its energy density changes over cosmic time, void expansion rates deviate from this pattern in ways that DESI's precision data can potentially detect. This makes voids one of the most powerful probes of dark energy available to observational cosmology. Combined with other probes, supernova distances, baryon acoustic oscillations, weak gravitational lensing, the void expansion statistics from DESI and Euclid will provide the tightest constraints yet on the nature of dark energy. The Boötes Void, the most extreme void in the observable universe, is a particularly powerful data point in this analysis. Its properties place unusually strong constraints on the models, because anything that can produce a structure this large and this empty must be consistent with everything else we know about the universe. The picture that is emerging from these latest observations is nuanced. The Boötes Void is real. It is large. It is deep. It is at the extreme end of what standard cosmological models produce, whether it requires new physics, modified dark energy, non-Gaussian inflation, or something more exotic, or whether it is an extreme but allowed statistical fluctuation in lambda CDM remains genuinely uncertain, and will remain so until JWST completes a deep census of faint galaxies within the void, and until DESI's full dataset has been analysed. What is clear is that cosmic voids in general, and the Boötes Void in particular, are not merely interesting curiosities. They are precision instruments for cosmology, probes of dark energy, tests of inflation, laboratories for galaxy evolution, and windows into the far future of the universe. The Great Nothing is not nothing. It is one of the most scientifically rich regions of the observable universe. We have spent this documentary exploring one void, the most famous void, the largest void known, the void that stopped Robert Kirshner's map-making cold in 1981 and has been puzzling cosmologists ever since. But let us step back and ask the broader question: what are cosmic voids, in general, telling us about the universe? The most striking fact about voids is how much of the universe they occupy. Not in terms of matter. Voids contain only a small fraction of the universe's mass. But in terms of volume, voids dominate. Approximately 80% of the observable universe by volume is void space. 80%. The cosmic web, the filaments, sheets, and clusters where most galaxies live, where most of the universe's matter resides, occupies only 20% of the available volume. We are, in a physical sense, exceptional creatures. We live in the 20%. Most of the universe volumetrically is the great nothing. This has a philosophical dimension that is worth dwelling on. When we think of the universe as a place full of stars and galaxies and wonders, when we look at images from JWST and marvel at the density of objects in every field of view, we are seeing the 20%. We are seeing the cosmic web, the filaments, the clusters, the extraordinary richness of structure that gravity has assembled over 13 billion years. But 80% of the universe is none of these things. 80% of the universe is void, vast, dark, cold, nearly empty volume. Cosmic voids are teaching us, perhaps more clearly than any other astronomical observation, that the universe is fundamentally a place of emptiness punctuated by islands of structure. The galaxies, the stars, the planets, the life that we know, all of it is the exception. The rule is the void. Voids are also teaching us about the nature of dark energy, the dynamics of void expansion, the way voids grow and evolve under the influence of the cosmic dark energy, provide direct measurements of dark energy's properties that are complementary to all other observational methods. As Deci and Euclid build ever more detailed void catalogues, and as the theoretical models for void evolution are refined, voids will become one of the primary tools for understanding the most mysterious component of the universe. Voids are teaching us about galaxy formation and evolution. The void galaxies, those isolated, pristine, environmentally uncontaminated systems that formed in the interior of regions like the Boötes Void, are among the most scientifically valuable galaxies in the universe precisely because they are the simplest cases. They evolved without interference. They offer a baseline against which the effects of environment, the mergers, the tidal stripping, the gas infall and expulsion of the cluster environment can be measured. Voids are teaching us about inflation and the early universe. The size and depth distribution of cosmic voids is sensitive to the initial conditions set during inflation, non-Gaussian primordial fluctuations. Deviations from the simple Gaussian statistics predicted by the most basic inflationary models would produce a different void distribution from the Gaussian prediction. The Boötes Void, at the extreme end of the size distribution, is potentially a fingerprint of non-Gaussianity in the primordial fluctuation field. And voids are teaching us, perhaps most importantly, about our own cosmic position. We live in the KBC Void. We are void dwellers. Every measurement we make of the local universe is conducted from within a region that is 30% underdense relative to the cosmic average. The Hubble tension, the persistent growing discrepancy between different measurements of the universe's expansion rate that has been one of cosmology's most urgent puzzles for the past decade, may be, at least partly, a consequence of this local underdensity. We may be systematically misinterpreting the universe's expansion rate because we are measuring it from inside a hole. This is the deepest lesson of the void, that where you are matters, that the universe is not the same from every location, that the cosmological principle, the assumption of homogeneity and isotropy on large scales, while a useful approximation, is not an exact description of the reality we inhabit. The Boötes Void is an extreme demonstration of how different the universe can be from place to place. And our own position inside the KBC Void is a more modest demonstration of the same truth. The universe is lumpy. It has structure. It has preferred regions and empty regions, dense nodes and vast voids. And understanding where we sit in this structure, understanding the cosmic address not just in terms of which galaxy and which star system, but in terms of the large-scale web of matter and emptiness, is essential for interpreting what we observe correctly. The great nothing is not nothing. It is the universe showing us something real and important about itself. something it has been trying to show us since Robert Kirshner's map went blank in 1981. Something we are only beginning, with the tools of 2026, to understand. In 1981, Robert Kirshner was building a map. He was not looking for anything in particular. He was doing the necessary, unglamorous, painstaking work of science, measuring one galaxy at a time, recording one redshift at a time, slowly filling in a picture of the three-dimensional universe. And the universe handed him an absence, a spherical region, 330 million light-years across, 700 million light-years from Earth, in the direction of the constellation Boötes, where the galaxies were almost entirely gone. Where 2,000 galaxies should have been, there were 60. Where the cosmic web should have been, there was the void. He called it the Great Nothing. And he was right. More than 40 years later, we know the Boötes Void better than Kirshner could have imagined. We know its diameter, its depth, its internal structure. We know the 60 galaxies that survive within it, and the particular way they are arranged. We know it is consistent, mostly, with the standard model of how voids form through gravitational void merging. We know that dark energy drives its expansion. We know that JWST is beginning to find faint galaxies within it that previous surveys could not see, and we still do not fully explain it. The depth of the Boötes Void, its near-total lack of galaxies, sits at the edge of what standard models comfortably produce. The 2025 research suggests it may encode signatures of primordial non-Gaussianity, fingerprints of the inflationary era. The census of galaxies within it is incomplete, and the true count may change the picture when JWST delivers a more thorough inventory. The jury, as the scientists themselves say, is still out. What the Boötes Void ultimately represents is not a problem to be solved and set aside. It is a permanent reminder of the character of the universe. The universe is not obligated to be full. It is not obligated to be uniform. It is not obligated to be comprehensible at first glance. 80% of the universe, by volume, is void. We live in the 20%. We evolve to see the structure, the filaments, the clusters, the light. We have no sensory apparatus for the void. We cannot feel it or see it or touch it from here. It requires mathematics and photographic plates and spectroscopes and supercomputers to reveal it. But it is there. 330 million light-years of nearly empty space. 700 million light-years from where you are sitting right now. The largest hole in the observable universe that we know of, a region where the cosmic web falls silent, where the lights go out, where billions of years of gravitational evacuation have reduced the galaxy density to 3% of the cosmic average and left. In the middle of the universe's most intricate structure, a space that is almost nothing. The silence has a name, the Boötes Void, the Great Nothing. And it has been there, waiting to be found, since the universe was young.